So today we'll be talking about quantum machine learning. You may recall I had an episode on quantum software engineering, and there I talked about the complementary strength of quantum and classical systems. And one example of a combination of quantum and classical systems are quantum machine learning systems or software. So they kind of replicate everything that you have seen in machine learning, but in the quantum space, and I'm going to explain that. So let's start with the quantum bit. So quantum machine learning is obviously quantum plus machine learning, right? And it literally is very often a combination of classical machine learning techniques with some quantum bits added to it. Let's start with what quantum is, just to recall the basic concepts. So if you look at classical software, classical algorithms, classical machine learning, your data comprises bits, right? So and you can think of a bit as a vector that can point either, say, upwards for 1 or downwards for 0, right? So these are the two values of your data. And of course, you have very large strings of these bits representing your data. And of course, you will have several data points to be represented. Now, when we go to quantum, you see a very natural extension of this. Rather than having only bits that point upwards or downwards, you can think of a single qubit. So if this were a bit, a qubit would be just not like a bit, but instead of only pointing upwards or downwards, it can point to anywhere on the surface of the sphere, right? So this can be any arbitrary qubit q. And once you look at it, once you measure it, it will fall down to the basis of your measurement, say 0 or 1, with a probability that is proportional to this angle. So your data can represent now not only 0 or 1, but can simultaneously represent any linear combination of 0 and 1 by pointing at any arbitrary point on this sphere. This is called a block sphere. And this is the first principle that gives you some level of, say, parallelism in codes, because you can operate on data that are on a superposition state. So they represent both 0 and 1, a combination of 0 and 1, a linear combination of 0 and 1 in a single state. So that's already quite something, but that's not sufficient to give you quantum advantage. Another important principle is that if you have a number of these qubits all pointing to a place on the block sphere, they can be entangled to each other using certain operations. So we'll talk about those operations a bit later. And the entanglement of these two qubits, let's call this one Q0, this one Q1, will give you a power of operating on one of them and having non-local effect on the other. So you're simultaneously calculating on Q1 and Q0 by doing a local operation on one of them. And also once you measure them, they will fall onto the basis of the measurement of the basis that you have chosen. And it could be a partial basis. There is a discussion about that we can discuss separately. So you will have entanglement, which gives you another source of, say, quantum parallelism in this case, which allows you to do operation on one qubit and then have an effect on the other. And what is very important is that the space of two entangled qubits cannot be classically simulated by n separated qubits. You need a much higher dimensional space, exponentially larger dimensional space to simulate the behavior of entangled qubits. So this higher dimensional space is key to the effectiveness of quantum machine learning. So let's see what quantum machine learning is. Suppose you have classical data. Suppose you have a data set of patients, for example, that have shown certain symptoms. You want to have at the end some sort of labeling, say a classification in terms of a certain disease, whether the result is positive or negative. That's what a machine learning model is supposed to do for you. What you do in the middle for a quantum machine learning model, you first embed this into your quantum space. And that embedding, which is called feature embedding, and the term is not specific only to quantum, any higher dimensional embedding could be called a feature embedding, will give you access to a higher dimensional space, which allows you to explore the correlation among your data points much more effectively, okay? So this is a mapping that takes you your data from a classical space, which is a lower dimensional, to a quantum space of qubits, potentially entangled qubits, and some of these feature embeddings actually do produce entanglement. And that allows you to operate in a much higher dimensional space. And then you apply the principles of machine learning, but this time on quantum computing principles. So quantum algorithms are typically represented by a circuit operating on a number of qubits. Okay, so you have, say, n qubits in your quantum space. You can apply a number of operations. Think of them as, say, AND or XOR in classical setting. These have different names and do different things. For example, it's called Hadamard. You can also produce entanglement by having gates that operate in on more than one qubit. This is called a CNOT. So it's represented like this. So this will already create an entanglement between your data and do operations. But you can also have parameterized gates. So you can have a gate that, for example, rotates one of your two entangled qubits with a certain angle, okay? And this angle is a parameter to this circuit. So these parameterized circuits are called variational circuits, or sometimes they're called ansatz. And what you do, you do your usual training. For example, you label a set of training data, a set of testing data. You do your usual training by optimizing the parameters of these variational circuits. You can also combine this with a number of layers of, for example, classical neurons, a layer of variational circuits followed, for example, by a classical neuron. And this will give you something called a quantum neural network. Of course, there are lots of different architectures. I don't have time to go through all of them, but quantum neural networks are just one class of quantum machine learning.
If you have these different layers in a sort of quantum neural network between classical and quantum, that transfer between classical and quantum, how many times do you do that? How difficult is that to connect up?
That's a very good point. So once you do all these operations in the quantum space, in order to bring it back to the classical space, you have to do measurement. And measurement is typically drawn as a kind of a dial, right? So I'm not very good in drawing, but you have a dial kind of gate. It's actually not a usual gate. It's a slightly more sophisticated type of gate that basically measures your quantum data and brings it back to your bits with a probability that is proportional to the angle of your data. And you typically do that a number of times to get a sense where your actual outcome lies, right? So for that, you need to repeat this process.
Because it's noisy and you have to do it a few times with...
Not only that, but not only that, but also because quantum computation is inherently probabilistic. So in order to know where your qubits were, you need to repeat this a large number of times to have a sense of where your qubits were in the quantum space.
So it's not kind of a one-shot deal. You have to do it multiple times, and
You typically repeat that, and if you were to reconstruct the qubits precisely, you have to do a huge number of shots. So typically you don't do that. You're typically interested in some property of the quantum space. And typically you can economize on the number of shots because you don't reconstruct the entire state, but you get a sense where in my block sphere approximately my qubits.
You have to be practical about it. Okay.
Okay. Right. Yeah. So that was about the general kind of scheme of quantum machine learning. Maybe what we can do, we can also look at one specific class of quantum machine learning models. And I've briefly explained what the idea of quantum computing is. So I'm not going to repeat that here, but I will briefly go through the idea of support vector machines. There are good tutorials out there that you can watch about the classical notion of support vector machines. And then I will explain what benefits you get by operating on qubits rather than operating on bits. So the idea of support vector machines is quite simple. Suppose I have a two-dimensional space and my data set is organized in terms of blue labeled and red labeled data, okay? So assume that, for example, my blue labeled data are positioned in these places, and I have red labeled data that are over here. Then in order to build a machine learning model that can separate future instances of blue and red labeled data and give me the correct label, this is called the classification problem, I typically draw a line that has the maximum distance between the blue and red dots, the data points, close to this line, right? Okay, so I can, of course, draw many different lines, but I try to draw the line that maximizes the distance to the blue and red dots that are close to this boundary.
So it's the most kind of in the middle as you possibly can.
As much as you can, right? This is good if your data behaves nicely in 2 dimensions, but very often you have data that that in its original representation cannot be separated so nicely. So suppose instead of this representation, my representation of blue and red dots are like this, and then there is no line in two-dimensional space that can separate them, right?
Not a straight one anyway.
Yeah, of course, yes. And the trick to classify this type of data is to move to a higher dimensional space, very much like the feature embedding that I talked about in the quantum neural network setting. And for example, if you look at this example, what I can do, I can go from two-dimensional space, if this is x and y, by keeping the x and y of my data constant. So if this is x and this is y, I copy the x and y from the previous dataset constant, and I define the z value of my data based on the Euclidean distance to the origin for all dots, right? That will give me, for example, something like this for my 4 red dots, and somewhat higher values for the blue dots in a three-dimensional space. Sorry, I'm not very good in drawing in 3 dimensions, but let's assume you can think of it as a higher dimensional space where the blue dots are a bit higher up than the red dots. And once I move, once I do this feature embedding, right? So this feature embedding that embeds my two-dimensional data into three-dimensional data, I can do the same calculations that I did for calculating this line, but in a higher dimensional space, and then I can calculate a plane in a three-dimensional space that nicely separates these, for example, just by an orthogonal plane to the z-axis, right? You can see that this nicely separates the two data that I have. The caveat is that the calculation of this plane happens in three-dimensional space rather than two-dimensional space, right? And in practice, you have to go to a much higher dimensional space, and calculating these things can become a bottleneck. So it doesn't scale up to a much higher dimension, especially if your data is already highly dimensional. You want to do the support vector machine on a much higher dimensional space. This calculation of feature embedding doesn't work. So people have thought about this classically and have come up with something called a kernel trick. So a kernel trick allows you to avoid calculating the actual hyperplane precisely and doing the precise calculation. Instead, you calculate a function k that represents the properties of the plane that separates these two classes of points. So this has all been done in the classical setting, but quantum already gives us a very nice feature embedding because we already know how to map classical data into quantum data, which is much higher dimensional, using standard circuits. So there are standard circuits that take your data and, for example, based on the angle in your quantum space, can map your bits and map them into the quantum bits using the angle as an additional dimension of your data.
Okay, you use the angle as a dimension rather than as a probability. Okay.
No, the probability is still there, but you use that to give another dimension to your classical data. There are also feature embedding that not only take your data and then put it in n qubits, but also entangle them and then use the entanglement space to encode your data in a higher dimensional space. So if you want to look them up, for example, there is something called a Z feature embedding. There is a ZZ feature map, right? So ZZ feature map, which also use, for example, ZZ feature map also uses a very similar scheme than what I represented before in terms of a quantum circuit that does entanglement together with superposition to represent classical data into a much higher dimensional space. So that's already one advantage, that maps your data to a higher dimensional space and allows you to do separation in the higher dimensional space provided by quantum data. But also, the kernel function can be calculated much more efficiently in quantum space. The kernel function, if you look at the classical definition, is calculated using something called a dot product of matrices. And dot product of matrices in quantum space is calculated much more efficiently by basically taking your feature mapping and inversing that in terms of a quantum circuit. So basically you are going to calculate your kernel by taking the feature map of one element of your data set, and then the reverse feature map of your other data set, and combining these two circuits together. And in quantum space, this bigger circuit will automatically calculate your kernel function. So the kernel function in the quantum setting is calculated more efficiently for certain types of data. And there are papers that show that for certain types of data, this is going to give you polynomial advantage in terms of training over the classical counterpart. So there are theoretical results out there that show some potential advantage. Whether we'll see practical advantage, that's something that we have been looking in our research for quite some time in practical data sets, for example, from biology, to see whether data from different types of disease, cellular mechanism in different disease, we can use quantum machine learning models to realize this type of quantum advantage. And that's an ongoing quest. We don't have the final answer to that question yet.
I mean, part of that you mentioned kind of a matrix multiplication, and my understanding is that's something that modern GPUs can do at high speed in very, very parallel fashion. Is quantum still going to be better than that? So
theoretically, first of all, quantum is moving very rapidly, but also classical techniques are moving rapidly as well, and it's difficult to predict where this race will end. As I said, in the future, we are very likely to have a combination of quantum and classical together. For example, many of these quantum neural network architectures use GPUs for the classical part, and then you combine them with a bit of quantum computing in the middle, and then it could be followed again by GPU computation. What is important here is that there is some proven theoretical advantage for certain types of data, and it's unlikely that this is going to be for huge amounts of data doing like huge data, big data processing, but it's going probably to be about very specific types of distributions of data. For example, when your data has a particular noise characteristics because of the way it's being gathered, because, for example, the classes of data are distributed in a very special way. There are very, very rare events in your data that cannot be detected easily using normal machine learning techniques. So what is going to happen is that you will find specific types of data for which quantum is going to show advantage that cannot be replicated classically. But we haven't yet we haven't yet characterized exactly what type of data we should expect this type of advantage.
I thought we could talk about Shor's algorithm today. So it's a quantum computing algorithm famous for its ability to theoretically break some of our crypto systems. But because quantum computing is not my thing, I've run over to the School of Physics to get some actual expertise.
Yeah, so I'm